Okay, this week we're going to start talking about heat and temperature. Temperature is basic, one of the things we all talk about all the time. Uh, for example, right now I don't have air conditioning in the upper part of my house. It's kind of hot up here. The lower part's nice and cool with the air conditioning. I have two units, but the upper part is actually got up to 90 degrees in the upstairs yesterday. So that would be a kind of thing that we all discuss temperatures every day. We think about what we're going to wear based on temperatures. Think about whether we're going to be outside. I mean, if the temperature is 30 below zero, I don't think we're going to be outside that much. And maybe if it's 95 degrees, you don't want to be outside too much, or 100. So temperature is something we need to talk about and understand a little bit of it, how it impacts the atmospheric circulation. So, so what are some of the causes and all of heat transfer? Solar radiation brought all this energy to Earth. All this energy has to get transferred around. It's transferred by heat. So, one of the hottest places in the world is Death Valley. We've heard it in the news about it reaching 130 degrees here this year, and they're working on verifying that. But why is it so hot there? Well, think about it. It's below sea level. So if you look at the curve on temperatures as you go through the atmosphere, remember it cools with height in the troposphere. Well, it also warms as you go lower in the troposphere. So if the atmosphere has gone below sea level, which Death Valley is, it's actually going to be hotter than a point that's at sea level. Also, it tends to get really good solar radiation. There's not a lot of clouds there, so it has an intense solar radiation. And the circulation there pretty weak, so you don't get a lot of mixing of air. So all that produces one heck of a hot atmosphere there. So we need to understand what temperature is. Temperature is directly proportional to the kinetic energy of atoms or molecules. What the heck does that mean? Well, atoms and molecules all vibrate. The faster they vibrate, they have more kinetic energy. They're moving faster. Motion is kinetic energy. So when they're moving really fast, your temperature is higher. When they're moving very slowly, the temperature is lower. Internal energy encompasses kinetic energy and potential energy. So it's a little different than just temperature. Heat is energy in transit. In other words, when energy is moving from the stove to the hot water that's beginning to boil, that's a heat transfer. So we're going to discuss how heat is transferred a lot in this section. There's also something called a temperature gradient. And guess what? The atmosphere hates gradients. It hates them in pressure, it hates them in temperature, it hates them in moisture. So it's going to try to get rid of a temperature gradient. Well, it comes right out of the second law of thermodynamics. Heat must flow in response to a temperature gradient, and it flows towards lower temperature to eliminate that gradient. So anywhere that one area of the atmosphere is warmer than the other area, the heat is going to want to transfer towards that warmer air. So there are things that transfer heat. Radiation. We talked about radiation warming the earth. Well, it also cools the earth. Conduction. We'll talk about that. Convection. Latent heat. Oh yeah, phase changes in water. Have I confused you yet? There's a lot going on here. So let's talk about radiation. We've talked about radiation both absorbing, coming in and gets absorbed by an object, which transfers heat to that object, and objects also radiate heat back out. The earth radiates heat out. So there's radiational cooling that way. So you have radiational heating and radiational cooling. Another one is conduction. All right. The Earth's surface can get pretty doggone hot. I don't know if you've ever seen people trying to boil eggs sometimes on the Earth's on a blacktop surface or whatever, or cook an egg. But the Earth, when the Earth's surface is dark, it's going to absorb radiation, get hot. Now, how does it get rid of that heat when it wants to transfer back? Remember, we want to get rid of the cold spots. When the air temperature is above it, it's a little cooler. So it's conduction. Think about it in the wintertime. You've all seen the signs for 32 degrees. Bridge freezes before the road does. Why the heck is that? It's due to conduction for a lot of it. Think about it. That bridge on both sides of it has air that is well below freezing, possibly, maybe in the 20s. So that bridge is, through conduction, is losing heat, both on the top of it, on the bottom of it. So it is cooling fairly fast. Take the road, on the other hand, the ground's probably not frozen, so the temperature is maybe 35 or 40 in the ground. On top of the road, maybe the temperature is 20 degrees, but the ground's absorbing some heat, pulling the heat up into that road. So the road is actually getting warm from below and cooled from above. So it can't cool as fast as that fabulous bridge did. So that's why you see those signs all over the place. Bridge freezes first. Convection is another process. Ever watch bubbles when you boil water? They go up to the top. That's convection. It happens in the air as well. Air gets hot at the surface, rises up and cools, gets cold, begins to sink back down. And that's convection. So sensible heating, what we call sensible heating, is a combination of conduction and convection. That's how a lot of the energy is transferred within the atmosphere. Latent heating. Here we go. Believe it or not, water, that 4% or less that it makes up, contributes a tremendous amount to little changes in temperature that can have a big impact on maybe whether you see snow or whether you see rain. Water, it takes a lot of energy, a lot of heat transfer to make it evaporate. So if you have a pool of water, a puddle after a rainstorm, and the sun's out bright, that day is going to be slightly cooler because all that sun's energy is going into heating that water, evaporating it, and sending it back into the atmosphere. Now, if that ground was really dry, we're in a period of drought, there's no water to heat, so more of that sun's energy is going into heating the Earth's surface, which then goes into conduction and convection and heats the atmosphere more. So when we've had a lot of rain, we tend to be a little bit cooler. When we've had less rain, we're not as cool. So you can see here, heat must come in. Think about it. If you're going from a liquid state to a vapor state, the molecules are moving faster in vapor. They're not as close together. Now, if you go the other way and go to solid, well, guess what? They're getting pulled together. So all of these things are ways of heat being transferred through latent heating. And right here, for example, if you have evaporation, you're causing water vapor to enter the atmosphere. The water vapor eventually condenses, forms clouds. So at that point, it's lost some heating. Some of that heat has got to transfer from the water vapor out into the atmosphere. It actually warms the atmosphere. Oh yeah, then you're going to go to another point at which liquid freezes. There's more heating lost. There's more energy lost. So that actually can warm the atmosphere as well. Now you go the other direction, if you have melting. Well, it takes some heating to do that. So heating is pulled into the liquid, into the water, and the same holds for evaporation, which we just talked about. So all this latent heating goes on through the atmosphere to change the temperature within the atmosphere. And specific heat, the amount of heat transferred into an object to make something happen, is huge in water. By far the biggest one of almost anything on Earth. And that's what impacts maritime and continental climates. You live in Ohio, you live in a continental climate. Kind of similar to St. Louis. You'll notice it gets pretty cold in winter, it gets pretty hot in summer. But look at San Francisco, which is in a more marine climate. Water takes a tremendous amount of energy to heat, so it doesn't get as cold or as warm as the surrounding land. So what happens? It keeps the temperatures moderate. I see it here in the wintertime or in the springtime sometimes. Water can get fairly cool off my coast here, and temperatures go down into the 40s at wintertime. In the spring, then, when I'm starting to warm up, if the air is coming off the water, hey, I'm cool. I stay in the 50s. Now, in the fall, that water right now, for example, is in the 70s here, well up in the 70s. So what happens in the fall, even though if it gets cooler, if I can get a breeze off the water, I'm still going to be close to 70 or in the 70s because the water then is warming me. So you can see water has a huge impact on marine climates. You happen to be, you could call it lucky living away from the water, or not so lucky. There's a heat imbalance at the Earth's surface. Absorption of solar radiation is greater than the emission of infrared radiation. So therefore, the Earth, you would think, would be going and continually warming. But no, the Earth is constantly transferring that heat into the atmosphere to make up the difference. And that transfer is what causes weather. And here you can see just a small depiction of that. Here comes your incoming solar radiation. Oh, some of it's scattered, some of it's absorbed, some of it's absorbed by the Earth, some of it's reflected from the Earth. And long wave radiation, all of that happening. So there's a complex energy balance within the Earth atmosphere system. Heat transfer being conduction and convection are sensible heat, and they can be measured with a thermometer. And you can actually see temperature changing. So here's Yuma, Arizona, very hot, dry place. There's not exactly a lot of latent heat going on out there, is there? But there is some heat stored in the ground, and there's some sensible heating, and that radiation is actually greater here than should be. Here you have latent heating, Madison, Wisconsin, more crops around, more moisture, more latent heat. So you can see the difference on climates around the Earth when you look at the Bowen ratio. And there's a surplus of absorbed radiation down towards the equator and even down to almost to our latitude, particularly in the summertime. But there's a deficit up to the north. So what's the atmosphere trying to do? Remember, heat is flowing towards the colder places. So all this heat has got to figure out a way to get up to smooth out this curve. That's done through air masses. It's done through storms. It's done through ocean currents. Are just some of the examples of the wings. We're going to talk about all of those throughout the course. Basically, an air mass is a big volume of air. It covers large areas of the U.S. or maybe Canada. Storms are another one. So all of this imbalance is what causes weather. And local temperature variations, you think about it. You live not that much further north than I am, yet you're a whole lot colder than I am sometimes because you're more inland and because you're less away from the ocean. But say you lived in Canada, think about it. Further north, latitude, less solar radiation, you're more of a deficit. If you live down in the tropics, more energy coming to you. And here you can see it even during the day. That's why we talked about the other chapter about the hottest temperature occurring in the late afternoon. Well, guess what? There's a surplus of energy coming in until right about 2, 3 o'clock in the afternoon. And then the outgoing energy begins to take over, and we begin to have a deficit of energy. So that's why your max temperature is there and your min temperature. You cool off fast in the evening, but then you slow down, and you wind up with a min temperature right around sunrise, or maybe even a little bit after sunrise when you get solar radiation peaking. Surface cover, high surface albedos like snow and all can reflect a lot of that energy away. And now we talk about cold and mass and air warm advection. We're going to look at that here in just a minute. Urban heat islands are another area. If you live in the middle of a city, you can really get a lot hotter than the outside areas of that city where there's more moisture, where there's more crops and all. So you can actually see they studied, for example, here, Washington, D.C. back in 2018. And hotter areas right downtown, cooler areas out just to the west or along the rivers. all the things we've talked about causing variations in temperature. So with that, let's just take a quick peek. I wanted to show you cold air advection. We have a weak cold front going through right now in Ohio. Along that cold front is temperature advection. So you can see right here in Ohio, all these lines of temperature connected right here, and the warming as well, of cooling off as moisture as well, drying. And that's just temperature advection. There's not a great wind flow here. It's not strong, but the winds are kind of perpendicular to it. The more perpendicular and the tighter the gradient of temperature is, the more stronger the temperature advection. And it can be warm, like it would be here, or it can be cold, like that. So that's all about temperature today. So I hope you got something out of that. And please ask any questions.